Okay, welcome back. How many Mountain Dew shirts did I have again? At least two. Uh, at least two, possibly three. Um, last time I'd kind of been on I'd been on a detour, going into a little bit of Greek math, just because it made sense to talk about prime numbers quickly. And one of the reasons for this is, as you'll see, I'm about to talk about Sumerian and Babylonian mathematics. Um, and you could say, well, okay, why do you need to talk about prime factorizations? The reason for that is because there's a strangeness to the choice of number base for the Sumerian and Babylonians. As I mentioned, this choice of number base is still with us. This is base 60 or sexagesimal uh, numbering system. It's still with us in the measurement of time, right? So the reason why I wanted to talk about prime factorizations before is because one of the reasons why it's believed that 60 was something that was chosen by the Sumerians and Babylonians it had to do with the fact that its prime factorization makes it really, really nice, okay, for a variety of reasons. So first of all, the way that this is styled uh, in our textbook and in general when talking about um, this topic is that the Sumerian culture was more ancient than the Babylonian culture. So the Babylonian culture eventually absorbed the older Sumerian culture. So the Sumerian civilization, I should say, this has ancient roots. I mean, in fact, part of the ancient Sumerian civilization were some of the city-states you've no doubt heard of, such as Ur or Uruk, which is the subject of the Epic of Gilgamesh, right? And so the Sumerian city-states are some of the oldest examples of human civilization that exist, right? So this is one of the oldest on the planet. Um, some of the absolute very first examples of literature or of, um, what we might call, human civilization. The humans, essentially, right? The agricultural revolution, basically. Humans arranging themselves into permanent settlements. There's only a few instances that are older than this and also have some form of writing. So Sumerian civilization is really, really old, and around 2000 BC, Sumerian civilization is. I don't mean to imply that this is some kind of like cataclysmic event or this is some big event. In fact, this is just by 2000 BC. Sumerian civilization has largely been absorbed uh, by Babylonians. Okay, and so the Babylonians, and there's a ton I could say here, but the time scale, you're looking at, like I said, right around 2000 BC, tends to be when the Babylonian culture is more dominant here. And so just quick geography mention. I don't have a map here, but so the Sumerian city-states were a little bit further south than the dominant Babylonian city-states. So anyway, but those were essentially brought into Babylonian culture around this time they become more or less indistinguishable. And so there are some artifacts of the Babylonian system. I don't mean literal artifacts. I mean, there are some things in the Babylonian civilization that are clearly brought over from the Sumerian civilization, and we don't necessarily have the best understanding of the maybe some of the original reasoning here. So for some of these things. So for instance, one of those is that the Sumerians had a number system that was base 60, or on a scale of 60, okay, which is called sexagesimal or sexagesimal. So sexagesimal system. And the Sumerian system had no place value, so no place value. Okay. However, the Babylonians adopted this. So I should say it's not. So technically, because they had no place value, it's not what we would call base 60 or technically sexagesimal. However, the Babylonians introduced place value into this system. So they kept 60 and introduced place value. So Babylonians introduced place value, thus having a true base 60 system. Okay. All right. And so, as many of you might know, many Near Eastern cultures, specifically the Sumerians and Babylonians, had a writing system known as cuneiform. So what is cuneiform? Cuneiform was a method of writing that involved taking a stylus that had been fashioned out of, I think, reeds, and making depressions into clay tablets that were still malleable. So making depressions in the form of wedges. So this is wedge-based writing. Okay. So this is one of the earliest writing systems on the planet. The idea was to, in fact, so Epic of Gilgamesh that I already mentioned was written in this way. So the tablets, so the tablets that the Epic of Gilgamesh was recorded on, the version of it that was actually recovered was from the library of Ashurbanipal, who was an Assyrian king. So Ashurbanipal had a library in Assyria. The tablets that formed the Epic of Gilgamesh were in this library, and they were this was written in cuneiform, so they were cuneiform tablets. So anyway, the idea was to make depressions in clay tablet, then set the clay tablet out in the sun for it to dry and harden into like a thing that could be permanently read, right? Because you had hard clay tablet, and these wedge depressions made made up their writing system. So I will use an approximation of the wedges here, and so let's say that we wanted to. So remember, this is roughly 2000 BC. So time scale here. This is roughly 2000 BC. So I'm going to specifically mention that some of this stuff was actually older than this. So some of this stuff was known prior to 2000 BC, but much of it wasn't introduced until later, or introduced until after this. So one of the around about this time. So keep in mind, this is in keeping. It's roughly contemporary with the two papyrus scrolls that we talked about earlier, the Egyptian, the examples of Egyptian math scrolls. So let's say that I wanted to write 35. Right? How would 35 be written in the Sumerian-Babylonian convention? So the way that 35 would be written is I'm going to use this symbol for wedges, so 3 to denote the 3 tens, and wedge symbols that look like this, they look like a Y, to denote the 5 ones. Okay, and so 35 would be written like this. Okay, and so it is a place value decimal system. Okay, and any number, say up to 59, could be written like this, right? So I can write numbers, from 1 to 59. Okay, can be written like this. Okay. So again, 12 would be written like this. All right, so there's 12. Okay. What about, say, 30? So 30 would be written like this. Okay. So why is 30 written like this? Well, this is 3 tens, right? For the digits place for, where we would put a 0, they just put nothing. Because they didn't actually have a symbol for 0, okay? And so they would write this. Now, here's where things get a little bit confusing. Okay, yeah, no 0, exactly, like I said in chat. So they had no symbol for 0 here. What if, so I said I could write every number from 1 to 59 like this. What about 60? How's 60 written? 60 is written like that. Okay. So that's a little confusing, because 60 is written the same way that 1 is written. Let's try to see what's going on here. What about, say, 60 to the minus first, right? Or 1 over 60, right? That's what we're talking about here. Well, that was also written like this. Okay, so this is definitely not good for our sanity here and trying to keep track of what it is that's going on here. What about, say, 60 squared? All right, so 3,600. That's written exactly the same way. So all of the powers of 60 are written like this. In fact, right, if we try to investigate this pattern, 60 to the 0 is, of course, 1, and that's written in the exact same way. So all powers of 60 are written like this. Well, that's very confusing, okay? In fact, in light of this, let's go back to these previous numbers that we wrote here. So for instance, so 35, that's a little bit crappy. I won't do that one. But 30, is 30 actually 30? Well, I wanted to write 30, so I wrote it like this. But if you were Babylonian and you see this, what does this mean? Well, this means 30. But because I have no symbol for 0 here, And because it's base 60, I'm resetting, right? Every power of 60, I reset, right? So I can, my places are kept track of from 1 to 59, but when I get to 60, I reset, right? So when I get to 60 times 60, well, then that's 60 squared, right? And when I would get to 60 times 60 squared, that's 60 cubed, so I'd have to reset again. And 60 cubed would also be written using the same symbol. So what is 30, again, or sorry, what is this symbol? It could be 30, or it could be 30. So this could equal 30, or it could be, say, 30 over 60. Right? So it could be 30 times 60 to the minus 1, or 30 over 60, which is 1/2, right? So this symbol could mean 30. It could also mean 1/2, or 30 over 60. That's not it. I mean, it could mean more than that. It can mean 30 over 60 squared. Right? It could mean 30 times 60. Okay, or could mean 30 times 60, or 30 times 60 squared. Okay. All right. So there's ambiguity here with what this symbol means. Similarly, 12, right? If I'm looking at this symbol, this could mean 12, so this is 12. Or it could mean, say, 12 over 60, which is 1/5. Okay. And so how did Babylonians make sense of this, right? How did the Mesopotamians make sense of this? Usually this would have been clear from context, right? So it would have been clear from context what things would have been meant here. Okay. So this is the idea, but of course this is, we're not used to having ambiguously defined numbering systems like this, but this is the idea. Okay. All right. And so this system, right, would eventually be translated over into Greek astronomy. Okay, so this base 60 system still lives with us, of course, and we'll see an explicit example of where, not just in the telling of time, but around, I believe, 150 BC. So this base 60 system was brought over to Greek astronomy in approximately 150 BC. So it was brought over to Greek astronomy, and this was done by Hipparchus. Okay, that's Hipparchus of Nicaea. In fact, today it still lives on in time and astronomical measurements. So to see how this lives on, consider the following. So to remove the ambiguities we had. So to remove the ambiguities from earlier, what do we do here? Let's say that we have this symbol, right? How would we write this symbol to remove ambiguities, right? So as we saw, this could mean 30, or it could mean, say, 30 over 60. Okay, well, those are very different numbers, right? Those are very different quantities. How do I keep track of what this means? Well, we would say that this means 30 degrees or 30 minutes, right? Okay. All right. Or what about, say, earlier I had the symbol. This is supposed to represent either 12 or 12 over 60, so which is 1/5. So in this case, we would say that this is, 12 degrees, right, or 12 minutes. Okay. And then lastly, what about, let's say I have a symbol like this. What is this representing? So here, this could mean, so this is 4 ones, right? And this is 2 tens and 1 60. So this is 60 plus 24. So this is 84, right? But what else could this mean? This could be 84 60ths just as well. So, or 84 60ths, which is 7/5. All right. So how would I express this using degrees, minutes, or seconds if needed? Well, this would be 1 degree and say 24 minutes, or could be 1 minute and 24 seconds. Okay. All right. Could be either of those things. All right. So this is how ambiguity was removed in this system. So this is the sexagesimal system. All right, so base 60. All right. Now, this is still really, it seems really cumbersome to work with, of course, for us, you being used to base 10. But this is surprisingly, this is a lot better to work with than a lot of ancient number systems. So, in fact, there are plenty of number systems that came after this that were in many ways a lot harder to do mathematics with than this base 60 system. Okay, it might seem strange to us, but it is still, a true base 60 system. There's place value, and once you nail down these problems with ambiguities, it takes some getting used to, but it's really perfectly fine. And so here's the big question, right? I mentioned why 60? Where would people come up with 60? So I've heard some discussion of this. People have brought up the fact that if you have a hand and you count with one hand, so not with two, what is something that you could do here? You could count on your knuckles using your thumb to count. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so you can count to 12 using one hand, and of course there's 5 fingers on one hand, and 5 times 12 is 60. Now, that might seem like you're really stretching, right? You're really, really just trying to come up with something to fit it to 60. And of course there's nothing special about 60 when it comes to that. You can always come up with some kind of weird rationalization for things like this. So absent any other evidence, that seems like total nonsense. But it turns out that apparently there are plenty of ancient civilizations in the Near East and in Asia that actually counted like this. This is how the counting was done. Rather than counting with fingers, the counting was done like this. Okay, and so it's not totally crazy that this would have been done. Now, what is another reason for a potential reason for 60? Ultimately, we don't know why 60 became the thing, and of course, there could not be a reason. It could just be that someone did this and someone else learned it this way and found it nice enough, and it just propagated from there. But one thing to note is look at the prime factorization of 60. So what's the prime factorization of 60? It's 2 times 2 times 3 times 5. So this is the prime factorization. Okay, so here's the prime factorization. What is nice about this? If I look at this and I ask myself, what are the factors of 60? Right? Well, my factors of 60 are, so factors of 60 are 1 and 60, right? 2, obviously 3, 4, 5, 6. These are all factors of 60, right? So 1, 2, 3, 4, 5, 6. What's next here? So 7's not, 8's not, 9's not, 10 is of course a factor of 60. Now, so now we have 12, right, and 15, and 20, and 30, and 60. Okay, so these are all factors of 60. It's really nice. I mean, first 1, 2, 3, 4, 5, 6. Those are all factors of 60. And what is nice about this is that any denominator, so any denominator in base 60 with a prime factorization involving only 2, 3, and 5 is going to terminate. What do I mean by that? Well, if you want to form a fraction, right, involving these base 60 things, that decimal, or the sexagesimal in this case, is going to terminate. It's not going to be repeating, i.e., it won't be a repeating sexagesimal. Okay. All right. So this gives a lot of potential denominators that are fine here, right? Anyway, 60. There's some number theory involved here where I could call 60 a much nicer number than maybe just a general randomly chosen positive integer. But 60 has a lot of factors, and this makes base 60 be not too bad. In fact, in many ways, there's a niceness here that's not really even present in base 10. Okay. All right. So, couple more things to note. So one, how did Babylonians treat 0? So, despite some claims that have been, I've seen some claims about Babylonians using 0 in some form before. So they didn't really have a symbol for 0. So they did not have a symbol for 0. Technically. That is, they did not have some symbol that was used to represent 0 that was always used to represent 0 in this way. Okay. they had placeholder. They had a placeholder symbol that could be used almost like a zero. Okay, so but they did have a placeholder notion. Okay, so what was their placeholder notion? So for instance, let's say we had this following thing here. So what was this? Right, placed in this way here. This was supposed to be 4 ones and then nothing here. This is a placeholder. And then 1 3600, right? 160 squared. So this is 60 squared plus 4 is what this was supposed to be. So this is 3604. And so the idea is that this placeholder notion is, of course, similar to the concept of zero, but they didn't treat zero as a number in this sense. Okay, so zero was not treated as a number here, and there was no single symbol for this. Okay, they just had this. They would, for the placeholder's sake, they would take one of these symbols and write it at an angle like this. Okay. Okay. And so it wasn't until so Ptolemy in 150 AD, right, replaced this placeholder with a little o. Okay. Possibly from the Greek. Word meaning nothing. Okay. All right. So while they didn't treat zero numerically or algebraically, they did introduce this placeholder position, which of course we use zero for that same purpose. Okay, so one thing I wanted to note, and then I'm going to go into this a little bit for the rest of class. Actually, I wanted to specifically mention some of this. So one, so Babylonians could divide by using that, say, A over B is the same thing as A times B inverse, and computing tables of inverses. Okay. So for instance, here is a table taken from, so the following table, maybe I'll write this. The following table is from a Babylonian tablet. So the tablet is, this is covered in Neugebauer, 1969. And so the tablet, or the table in question, is here. Let me bring this a little bit closer. So this has been translated into modern notation here, but basically the tablet, here's the B, here's the denominator, right? So 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, all the way here. And then 1 over B is computed. So 1 over 2, of course, is 30 minutes here, right? Or 30 seconds. 3 is 20 minutes. Because that's, of course, 1/3. So 1/3 of 60 is 20. 4 is 15 seconds, and so on. So all the way down to here. So 1/8. Think about this for a second. So 1/8 is 7. Let's see here. So this is a typo. There should be 2 of those here. So that should be 7 minutes 30 seconds, 6 minutes and 40 seconds. That's what this should be. So there should be 2 of these here, and here, just like in the next, just like in the next. The next lines here. So anyway, how to actually read these things. So of course it's tricky to us who are used to base 10, but the idea here is that you can translate this, of course, by paying attention to the fractions here. So this would be, so this is the fraction of 60, and then there's an additional fraction of 60 squared here, right? That ends it. So let's actually write out some of these. So for instance, B, I'll just write out. So here's B, here's 1 over B written in seconds, or written in this hexadecimal notation. So for instance, if B is 6, then 1 over B is 10 minutes. Okay, and so how can I write that? So the minutes are keeping track of, right, if we're writing this, so we're writing this as 1/6, which of course is 10 over 60, right? And that's exactly what this is referring to. Okay, and so what about something like, say, 30, right? This is written as 2 minutes, and of course 30 is, this is 1 over 30, which is 2 over 60, so that's what's written here. So what about something that's more complicated? It's like 9, right? So 9 is written as 6 minutes and 40 seconds. Okay, and so what we have here, of course, is 1 over 9. Okay, so what is this supposedly written as? This is written as 6 over 60, right, plus 40 over 60 squared, right? Does that actually work here? So so here this would be 1/10 plus 40 over 60 squared. So the question is, writing this as 1/10 plus 40 over 60 squared, that's 3,600. Right, so this is 4 over 360, or 1 over 90. So this is 1/10 plus 1 over 90. So what is this? This would be 9 over 90. Right, so multiplying by 9 here, so this would, 10 over 90. So this would be, 9 plus 1 over 90, which would be 10 over 90, which would be 1/9. Oh, I realize that everything is blurry. That is unfortunate here. Yeah, from where I was focused in on the book. Okay, so going through this again then. If my denominator is 9 here, then 1 over 9 was written, so this was directly from the table of inverses, so this was 6 minutes and 40 seconds. Okay, now we would write this as just 1 over 9. Okay, but what is 1 over 9? So 1 over 9 is, according to this, right, from this table, is 6 over 60 plus 40 over 60 squared. That's what these symbols mean. Okay, and of course 6 over 60 is just, so 6 over 60 is just 1 over 10, right? So that's just 1/10. Plus 40 over 60 squared is 40 over 360, which is 40 over 3,600, which is just 4 over 360, which is 1 over 90. Okay, so this is 1/10 plus 1 over 90. And so getting common denominator here, this would be 9 over 90 plus 1 over 90. So that's 9 plus 1 over 90, which is 10 over 90, which is 1/9, which is exactly what we're doing. Now, you might say, wait, this is circular, or either it's going in the wrong direction. The idea here is we were going in this direction because we were checking that this worked. Okay. Yeah. So Sophia asked, how did I know how did I know that this was the case? So I don't. I didn't. So I was checking this. So I was just reading from the table and then checking that this worked. If you wanted to come up with this, you would need to go in the other direction. Okay, you would need to go in the other direction, and the way that you go in the other direction is exactly, you know what your denominators for your system are, right? So your system is, you have a ones place, right? So you have you have stuff, right? So I'm just going to leave blanks here. You have blank times 60 to the zeroth place, and then you're adding to that something times 1 over 60 plus something times 1 over 60 squared. Plus here I would have something times 60 to the first, plus something times 60 squared, right? And so on, right? That's how your system works. That's what base 60 means, right? So you knew the denominators you're looking for. Once you know the denominators you're looking for, it's just a matter of writing 1/9 creatively and coming up with these denominators, okay? Right? Yes, exactly. So Ben's is saying, yeah, the single apostrophe denotes 1/60th, and the double denotes 1/60th squared. That's right. Okay. All right. And so this table again, and I'll remember to focus after this. So then this table was meant to be a nice, concise list of a bunch of denominators here and their inverses, right, written in this notation. Okay, so directly from this table, this would basically save you the work of trying to come up with what these things were and say, oh, okay, well, here's the inverses worked out for you. Okay. All right. Now, one thing to note here, note that every single B that is listed here is a number that's prime factorization, only involves 2, 3, and 5. Right? So why is that? Right? So like 21 is not listed here. Right? 7 is not listed here. Why? Because any of these B's, any of these denominators that don't have a prime factorization that only involves 2, 3, and 5 would get an infinitely repeating sexagesimal. Okay, now before you turn your nose up at that, of course we have to worry about this in base 10, all the same, right? So in base 10, right, we have 0.1 repeating, right? That's 1/9, and we have 0.3 repeating. We have 0.2 repeating. We have all those, and of course we have more complicated ones too, right? So 0.121212 repeating, right? That's a problem in base 10. There's no avoiding that, right? So you're not getting away from repeating decimals here. So anyway, so that's whoever the scribe that made this table, might have been afraid of repeating sexagesimals, and so they didn't get into that. One thing that I wanted to mention here, and I'll get a little bit more in detail with this maybe next time. I got time pretty much to finish it and start on the next bit. So the following. So Babylonians could extract square roots to a very accurate degree. Okay, what is the way that they could do this? So this is so this method is called Herons Method. This was named after Heron of Alexandria, who recorded it in 60 AD. But it was not due to him. The Babylonians did this. So he included it. So it is included in Metrica. was the work that he included it in, but this was known to the Babylonians. So in fact, one of the tablets mentioned here actually computes the square root of 2 that in the way that I'm about to show you. So how does this go? Okay, so say I want to compute square root of a. Okay, and when I say compute, I want to get some decimal, right? Or in this case, sexagesimal, right? I want to get some numerical thing that I can actually use to compute. Okay. So I want to get some numerical answer when I say compute square root, right? So it would be like me asking you to compute square root of 5, and what I mean is that I want you to give me, say square root of 5 to like 5 or 6 digits, right, in base 10. Could I move the paper up? Does it look okay now? I moved it up. So I didn't know what thing was missing here, so I moved it. I moved it up. Let me know if it doesn't look good. So say I want to compute square root of a. Okay. So how can I go about this? So the idea is what I do is I pick a rational number. What is a rational number? So a rational number is a fraction of integers, right? A ratio of integers. Okay, and so pick a rational number. We can't see the top. Is there a top? This? I'm trying to look on the on my YouTube feedback. I don't see. I don't know what my camera is cutting off, but I don't have anything written above this thing that I've underlined. Okay, so pick a rational number that is a ratio of integers. So 17 over 5. That's a rational number. So pick a rational number. Call it a sub 1 between square root of a and square root of a plus 1. Okay. And so if you say wanted to compute square root of 2, right, then this would be you picking a rational number between square root of 2 and square root of 2 plus 1. Okay. And so this gives you a window here. The idea is when you're computing a square root, you know roughly where it is, right? And the way that you know this is the following. So like, why do I know that square root of 2 is between 1 and 2? Because 1 squared is 1 and 2 squared is 4, right? So square root of 2 has to be between them, right? And I can even guess if it's going to be closer to 1 or 2, right? So the idea is, this gives you a window. You're always going to be able to pick something that is nice enough to work with here. Okay, and then what do you do? Okay, so then this is going to be an iterative process. So this is the first one you've picked. We call it a sub 1. All right, so then what do I do here? So let a sub n plus 1 be defined to be a sub n. So this is a sub n plus a over a sub n and all this is divided by 2. Okay. All right. Then what happens here is that a sub n goes to the square root of a as n goes to infinity. Now, if you haven't seen this notation before, what this means is that we have an iterative process here, and as we do more and more steps in this process, the numbers that get spit out of this get closer and closer to the thing that I actually want to compute here. Okay. All right. So I won't get into the reason why this works, but it works. And of course, the thing that I should say that I keep saying over and over again is that the Babylonians, of course, did not prove any of this. They just did the computation. So there was absolutely no proofs of any of this stuff. They were just doing it, right? There was no real explanation for why it worked. They were just showing that it did. Okay, through just doing a bunch of these computations. So for instance, let's do this. Let me move this up here. Okay, so I want to compute square root of a. All right, so let's do this as an example. Let's say that I want to compute square root of 2. Okay, if I want to compute the square root of 2, so a is equal to 2, and I can pick an a sub 1 between square root of 2 and square root of 2 plus 1. Okay, so I know that 3 halves is such a number, so I'm just going to pick one. I'm not necessarily saying that's the best. I'm just saying pick a sub 1 to be 3 halves. Okay, so let a sub 1 be 3 halves. Okay, then we form the next entry, the next term in this sequence, okay, by following this formula. So this is a sub 1, so that's 3 halves, plus 2 over 3 halves, all over 2. So what is that? So let's try to go through this. This would be 4/3 plus 3 halves. So I believe I'm just going to go ahead and write out rather than take the time to compute this. Turns out if you compute this, this is 17/12. Okay. All right, since I'm running out of time, I'll quickly do this. And if I compute, so a sub 3, if I compute using the exact same formula, I get 577 over 408. Okay, now if I write this in sexagesimal notation, what is this? This is actually a repeating sexagesimal. I'm not expecting you to know what's going on here, of course, so let's do it like this. So this is 1 hour or 1 degree, 24 minutes, 51 seconds, and so on. The next one I think is 35, yeah. So this is repeating, okay? This is computed in some way through blood, sweat, and tears, okay? And then a sub 4 is computed to be 665,857 over 470,832. And if we do that, we could put this in sexagesimal notation, okay, which is 1 degree, 24 minutes, 51 seconds. And then the rest looks something like this. So we're getting closer to the actual value supposedly here. Okay. In fact, you might say, why are you doing all this? What is going on here? In fact, this should be getting closer and closer to the square root of 2. In fact, the Babylonian Tablet the label of the tablet is YBC 7289. So the Babylonian Tablet YBC 7289, dating from 1600 BC, okay, gives square root of 2 as 1 degree, 24 minutes, 51 seconds, and then 10. What did they call these? I have to look up what the terminology was, at least the Greek terminology here. So it gives square root of 2 as this, which is very, very close. It's extremely accurate. In fact, if we had, so this a sub 4 here, which this is very close to, right, is like accurate to 23 digits or something. If we were to translate this into base 10, this is accurate to like 23 digits. Okay. And so this this approximation of square root of 2 that the Babylonians gave in 1600 BC, right, was very, very, very accurate. Okay, so Babylonian mathematics was extremely impressive, and a lot of this, especially the Babylonian algebra that existed, was kind of absorbed by the Greeks later. To some extent, it was absorbed by the Greeks. So anyway, we'll talk about that. Talk about that next time. So I will finish up with Babylonian mathematics on Monday, and we will start with the dawn of Greek mathematics, so the very early Greek math that was being done. So we'll very quickly get to the Pythagoreans. All right, and so that's that. I will see you all on Monday. Over the weekend, I'll post your first homework assignment, and it'll be some short writing assignment that has to do with what we've covered so far. Dan, make sure you want to play Civilization. Yeah, I mean, in the Civilization games, I always like in the tech tree. There's always a math tech tree, which usually I think usually once you have mathematics, you can build catapults and stuff, right? That's like the first thing you get, which is definitely a nice thing. But it turns out you can do a lot more than building catapults with it, right? Anyway, I will see you all on Monday.